Okay, we're going to, as I mentioned, continue lecturing here. So we're going to go off to the next chapter. We got two chapters to go, 2 days after this. Super good. So obviously this is not on our exam next week. Just chapters through chapter 17 should be. We're going to talk now about chapter 19. So we're going to talk about transition metals a little bit, and then we're going to talk about coordination compounds and complex ions, which usually involve transition metals. So we're going to do a little bit. First part here, hopefully, should be sort of review of some of these things from Chem 50, which then will kind of help you with sort of the second part of the chapter, which is our complex ions. So let's get started here. Um, Obviously, we are talking about transition metals to begin with, as they are really the main sort of metal we find in complex ions. And hopefully, we remember our transition metals should be found, obviously, in the middle of the periodic table. One of the things, as you probably remember and know, is again, transition metals can make a variety of sort of charges. That's why we use like Roman numerals when we name them in ionic compounds to indicate the charge that they could have. Although they can make a variety of charges, there are a few sort of transition metals that do have fixed charges, and that's your kind of three pack here of zinc, cadmium, hanging left there to silver. So zinc and cadmium do have fixed charges of +2. Silver has a fixed charge of +1. But pretty much all the rest of our transition metals through here will have a variable type of charge. Also, our sort of staircase kind of comes through here, and down on this end of it here, they're not technically transition metals, but they also have a variety of variable type of charge, things like lead, bismuth, and that sort of area. So we're going to talk a little bit about some, again, properties of these transition metals as they are the main part of our uh, complex ion. The first thing we're going to talk about is something you might have talked about before in Chem 50, and that's effective nuclear charge, which is Z effective. And Z effective is the effective nuclear charge. It is essentially the charge that electrons feel, that sort of positive attraction to the nucleus, based on whether or not there are other electrons present. So, a very basic, simple example of this is lithium. Lithium has 3 electrons, so it is 1s2, 2s1. This is electron configuration. As you probably also know, these guys over here in the highest energy level, that is what the 2 stands for, right? The 2 is the principal quantum number, or the N number. That is the valence electron out here in lithium. These are sometimes referred to as core electrons as they are closer to the nucleus and they're held tighter. So if we just kind of sketch what's going on here, say with lithium, lithium obviously has an atomic number of 3, which means overall its nucleus has a +3 charge as it has 3 protons present. Kind of on the first energy level, we have those core electrons. So we've got a couple of electrons. And obviously on the next energy level there, we have our valence electron out here. Now, one of the things you hopefully remember is the attraction between electrostatic attraction between positive and negative does increase with charge size. So the larger the charge size, the stronger they're attracted to each other. So if you had a +3 and a -3 coming together, they would be held together tighter than, say, a +1 and a -1 when they come together. So when we look at sort of our lower energy electrons here, those lower energy electrons are really close to the nucleus, and they feel really the full sort of brunt of the +3 attraction from the nucleus. So they're held pretty tightly. And as you probably know, right, that is why core electrons are not involved in bonding, right? Because they're very close to the electrons and they're held very tightly. Now, when we look at the outer electron or valence electron out here, he is experiencing what is sometimes referred to as shielding. And he is shielded from the full brunt of the positive charge by those lower energy electrons. So instead of that valence electron feeling the full attraction of +3 to the nucleus, it is shielded by those lower energy electrons and is not feeling as strong of an attraction. So it's kind of like, again, he sat down in the movies, had a nice, perfect view of the screen. And then, right before the movie starts, somebody sits down with a giant hat in front of you. You've now just been shielded at half of your screen, so you don't really see all that. And that's sort of the same idea here. So lower energy electrons can shield higher energy electrons from the full force of the positive charge. You could actually calculate Z effective by taking the positive charge of that atom minus the number of electrons that are providing shielding, and you get the effective charge that that outer electron is feeling. So instead of feeling an attraction to the nucleus of +3, it is feeling only a +1 attraction, which is not as strong as obviously our core electrons down here. So this guy definitely still feels an attraction, but it is much less of an attraction than those lower energy level electrons. The result of that is it's not going to be held as tightly. And again, that is why one of the reasons why our valence electrons are involved in bonding. They can kind of move and share a little bit easier than those core electrons. In general, if you look on the periodic table, the effective nuclear charge trend is it increases as you go up and to the right and decreases as you kind of go down and to the left. As you go to the right on the periodic table, the atomic number increases, which means the nucleus has a greater positive charge. And because of that, it's going to pull all electrons closer because even the effective nuclear charge is now going to be greater because you have a greater positive charge in the nucleus. And that brings an important effect on radius. And we can see that this is sodium, magnesium, we got aluminum and silicone. That is going through the third period there. The third period on the periodic table. And you can see that the effective nuclear charge increases as you kind of go to the right on the periodic table. And the result of that is, again, we actually see our radius of our atom gets smaller because of that. So because of the greater positive charge, the greater effective nuclear charge, those outer electrons, instead of being way out here, get kind of pulled in closer to the nucleus. And overall, the size of the atom also is affected by that. As you probably know, and I think we'll see on the next slide, but size, right, decreases as you go this way and increases as you go that way on the periodic table. It sort of follows our effective nuclear charge. Any questions on that there? And there is our size, again, getting much smaller as we go to the right, a lot larger as we're going down. There are our transition metals. As you may also know, down on the bottom is the lanthanide and actinide series, which technically go right about there if you follow the atomic number. And those are sometimes referred to as inner transition metals, as they kind of would go there technically. I've never seen a periodic table except in one place where they did that. And it took up the entire wall because they had to move everybody to the right in terms of the periodic table. But these guys technically go in that sort of area there. In terms of electron configuration, you may also remember that s orbitals, right, could hold 2 electrons, and group 1 and group 2 on the periodic table is our s block on the periodic table. Group 3, 4, 5, 6, 7, and 8. This is our P block, right? Coming this way. And the P subshell could hold a maximum of 6 electrons. 1, 2, 3, 4, 5, and 6, right? 1 and 2. And obviously here our transition metals is our D block, which could hold a maximum of 10 electrons if you fill up all the orbitals in a subshell. And again, you can just count it 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here, this is our F block, and that is 14 electrons. Each individual orbital, right, could hold 2 electrons. And a grouping of orbitals together is referred to as a subshell or a sublevel, depending on what you were taught. So, if you had something like P, like 2p, there's a px, a py orbital, and a pz orbital. All three of those p orbitals together make up the p subshell, right? And again, each one could hold 2 electrons. A reminder as well, in a subshell, right, they follow Hund's rule, right, which is maximizing parallel spin, which means they go in one at a time in the upwards division way and then come back and pair off afterwards, right? So they just don't go two at a time and they follow that. Also, right, when we look at an orbital in electrons, if these arrows represent electrons, they do not violate Pauli's exclusion rule, which means they don't have the same 4 quantum numbers, right? And if this was like we'll just look over here. This was like our 2p. I would also have an electron there. If we were doing quantum numbers, n would equal 2, right? L would equal 1, and m sub L would equal -1, and m sub S, which is the spin quantum number, would be +1/2. Yeah, you remember those things? Yes, they teach that still here, right? I hope. Yes. All right. So those are our quantum numbers, but Pauli's exclusion rule, right, basically means you can't have 2 electrons in the same orbital that have the same 4 quantum numbers. The way they get around that is the spin quantum number. If it is pointing upwards, it's +1/2. It is pointing downwards, the spin quantum number is -1/2, right? So that's sort of the way they kind of get around it. As this guy here would have basically pretty close to the same numbers, n equals 2, L equals 1. By the way, L is the angular quantum number. It basically tells you the type of orbital that's present. 1 represents a p orbital, 0 represents an s orbital, and so forth. M sub L would equal -1, and M sub S would equal -1/2 for this electron here. So, excuse me, transition metals. So similar characteristics within a given period and also within a given vertical group on the periodic table. When they do form ionic compounds, they can form more than one oxidation state, and they are oftentimes the metal or the cation that is present in the transition metal. And we have seen transition metals before. That is a metal ion that's attached to a bunch of stuff. We've seen the kind of funky formula when we did hydrolysis. You know, that was sort of like your copper with like your 6 waters with a +2 charge. That's basically like a complex ion type situation that's occurring here. And here is an example of that. So here's our cobalt in the middle, surrounded by these guys here. These guys are ammonia. These are what are referred to as ligands. And ligands are Lewis bases. And if you remember Lewis bases from the acid chapter, acid and base chapter, a Lewis base is a donor of electron pairs, right? It will donate an electron pair. And a Lewis acid is something that will accept an electron pair. And something that's good to accepting electron pairs are metal ions that have positive charges. Because they have positive charges, they have lost electrons, which means they're good at accepting electrons. They're electron deficient in this particular case. So that is a formula typical of a complex ion. Later on in this chapter, you'll know how to properly name that as hexamine cobalt 3 ion, and you'll be able to actually name that as well rather than, that thing over there with all the stuff in the formula. When we talk about ionic compounds, depending on the sort of metal that's present, it will absorb light differently, and they will sometimes see different colors that come out based on the complex ion that's present, the ligands that are present, and really the metal ion that is present. A reminder that when we absorb are the color that we see, for example, in a solution is the complementary color to the wavelength of light that's being absorbed. So when we see a red solution, it is not absorbing red light. That is why you set your spectrophotometer not to the red visible part of the spectrum. You set it in a different sort of area of the spectrum to the complementary color of red. A lot of compounds are paramagnetic. Paramagnetic means you got some unpaired electrons. Yeah, so electrons have spin, which does give the sort of compounds different properties. Paramagnetic means some unpaired electrons. Diamagnetic means you've kind of paired off a lot of your spins going in opposite directions. When we talk about spins and electrons, this arrangement here is what is referred to as being paired spins. They essentially kind of cancel each other out, with the spin here being plus a half, the spin here being minus a half in that case. Parallel spin is where they are all heading in the same direction. So that is parallel spin there. That's also paramagnetic. There's a lot of unpaired electrons sort of happening. Electron configuration, as you hopefully know how to write, but just a reminder, just in case it's been a while, right? We just went over a second ago. S orbitals could hold a maximum of 2 electrons. P subshell, 6 electrons. D subshell, 10 electrons. F subshell, 14 electrons. Remember that on the first energy level, there's only S's, right? It's not until the second energy level that you start to see p orbitals available, not to the third energy level that you see D's, not to the fourth energy level that you see F's. If you remember 1, 2, 3, 4, and that also allows you to figure out the proper electron configuration, because maybe you made a chart like this before where you go 1s, down to the right a little bit, 2p, down to the right 3D, down to the right 4F, and you basically just fill in the numbers underneath: 2S, 3S, 4S, 5S, 6S, 7S, 2P, 3P, 4P, 5P, 6P, 7P, 3D, 4D, 5D, 6D, and 5F. And you always start this way up here. And you follow the arrows. You zigzag back. One of the things people always screw up on is right about there, which is we do go from 3p, right? But remember that the 4s orbital is actually lower in energy than the 3d. So they get the electrons first, and then you go to the 4p, and obviously you could follow the pattern all the way across. You could just basically follow that through. Um, so when we write electron configuration, we always write it based on filling order, which, as I just mentioned, the S's do get the electrons first before the D's. Something else that you might remember as well, though, is once you start putting electrons in the d orbital, there's actually a switch in terms of the energy. And after you start filling those d orbitals, the 4s, for example, actually ends up being higher in energy than the 3d. And that's after you start putting those d orbitals. That affects, as we will talk about here in a second, what happens when they make ions, right? So when they make ions, because there's a switch in energy that occurs, they actually will lose their s electrons first when they are ready to sort of get rid of electrons. And then, if necessary, they will go into the d orbitals and take electrons out of there. So they do lose electrons sort of differently because there's that switch that occurs. But in terms of electron configuration, we do go in this order. And then afterwards, where we want to get rid of electrons, it does have that switch. This is also shorthand, right? And that is sometimes referred to as noble gas configuration. When you're doing electron configuration, in the box is the noble gas there, or the bracket, right, of the noble gas that comes before your element. So if you were doing something like sodium, which is 11, 1s2, 2s2, 2p6, 3s1, up through here. If you count the top numbers, that's how many electrons. That is 6, 2, and 2, which is 10. Go to periodic table. Number 10 is neon, which is a noble gas. And you put that in brackets and just continue on with the electron configuration in this case, which would be neon. Um, what we got there? Through I actually got to put the 3 there. I missed the 3. 3s1 happening here. So there are also some exceptions to if you follow this sort of chart. You will run into some exceptions. Probably the two that you were responsible to know was chromium and copper on the periodic table. Those two are exceptions. If you wrote the electron configuration for chromium and follow kind of this order, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Obviously, through here, that's 18 electrons. That is where the argon comes from. 4s2, 3d4 in this case. And it is found experimentally that it is more stable with one more electron up in the d orbital than in the s orbital. And that is the proper configuration here with one more electron in the d and one less in the s. And if you just think about that, it just kind of fills up and it really does maximize parallel spin there by putting a single electron in each. Copper is a very similar exception. It has one less electron in the s orbital and one more electron in the d orbital. In fact, if you look on the periodic table where chromium and copper is, and you go down and kind of in, there is a lot of those similar types of exceptions in the electron configuration. For example, PD has no electrons in the s. They've all been promoted there to the d orbitals. Silver is also an exception as well. There's a lot of exceptions in that sort of area, very similar sort of exceptions that occur there. Any questions on that there? All right. So as I was just mentioning earlier, um, we do see transition metals lose electrons differently, and that is because if we kind of go back to where's that periodic table here somewhere? There it is, right? We go to the periodic table and we think about valence electrons, right? It does equal the group number, and that also goes for our transition metals. But when we do our transition metals, we do the regular kind of 1 through 18 numbering through there. And that tells you how many valence electrons are available. So if we took something like iron, which is in terms of electron configuration, argon 4s2, 3d6. This is the 8 valence electrons that we see for iron. It is the 2 from the s orbital and the 6 from the d orbital. And so you want the number of valence electrons for transition metals, you should do the 1 through 18 numbering through there, and that will give you how many numbering. So what you see here is obviously transition metals could have upwards of 12 sort of valence electrons, but most of the time you would not use that because you don't usually see something with like a plus 12 charge or anything like that, right? So it won't probably lose 12 electrons along the way, but they could potentially do that. So when they do make ions, because of that, we do see a change in what is lost. So as it is filling, as I mentioned earlier, we will put the electrons into the S first and then into our D. And afterwards, there is a switch that occurs, and we will again see the 4S being higher than our 3D. So all transition metals will essentially lose their s electrons and then dip into your d if necessary. So here with Ti, which makes a +3 charge, that means it has lost 3 electrons. So these again are going to be the first two that go. And we are going to take 1 electron out of here, and we will end up with argon 3d1. So in this case, it has 1d electron available to it. Remember also, unlike representative metals, which in representative metals, when they lose electrons, they end up at noble gas configuration, right? They end up as isoelectronic with noble gases, which means they have the same electron configuration as noble gases. Transition metals don't typically end up at noble gas configuration in terms of their electron configuration because they have to lose too many electrons to do so. So if we looked at something like iron, which again is 26 electrons, it would have an electron configuration once again of argon 4s2 3d6. If we had iron that has a +2 charge, instead of 26 electrons, it's going to have 24. Once again, it's going to be these 2 electrons that go away, and we will end up with argon 3d6. So it would have 6 d electrons available to it. If iron made a +3 charge, it would have 23. At this point, we would take 2 out of there and now have to take 1 out of our d. That would give us argon 3d5, which means it has 5 d electrons. Any questions on that there? Okay. Let's talk about some other sort of transition metals sort of characteristics. Obviously, as we saw, and even we saw in the oxidation reduction lab, something like Mn could have a variety of oxidation states. And you can see it kind of builds up as you go from left to right here, kind of gets to the peak and then kind of comes back down. A vast majority, though, of common oxidation states for these guys, as you can see, +2, +3, but something like Mn, also like in that experiment, can have a variety of different oxidation numbers as you go through there. Ionization energy is the energy that is required to remove an electron, right, from the gas phase of an atom. Electrons do come off one at a time, as hopefully you remember. So if you took something like magnesium, the first thing that would happen is magnesium would lose 1 electron. And that is what is sometimes referred to as the first ionization energy. The energy basically to remove that first electron. Then magnesium that's already lost 1 electron would lose a second electron. And that's what's known as the second ionization energy. And maybe it continues on and it loses a third electron. And that would be the third ionization energy, right? So when we talk about ionization energy, we're talking about removing electrons. And when we remove electrons, we end up with cations or positive ions. So we oftentimes associate ionization energy with the formation of a cation or positive ion. Is it easier to remove the first electron or the third? Which one's easier? It is much easier to remove the first electron. First electron, you're neutral, right? When you lose an electron, the size of the cation gets smaller, right? The electron cloud shrinks. So that brings those electrons now closer to the nucleus, and they're going to be held tighter. If you remove the second electron, going to get smaller. Everybody's going to move closer to the nucleus and be held tighter and tighter. So the general trend is from the first ionization energy to the second, to the third, to the fourth, however many you want to go through. It gets harder and harder to remove those electrons, and the ionization energy increases as you continue through that process. In general, on the periodic table, as you go from left to right and down, the first ionization energy increases as you go up to the right and decreases as you go downward. If we take a look at magnesium in terms of its electron configuration, 1s2, 2s2, 2p6, 3s2, this is the three valence electrons. I'm sorry, the two valence electrons that it has, and these are our core electrons. So what happens is when we think about magnesium, you may be saying, does the magnesium always form a +2 charge? And the answer is, yeah, it pretty much does, because when we get rid of two electrons, we're now into the core electrons, which are super close to the nucleus and held really, really tightly. It takes a tremendous amount of energy to try to rip that electron off, and it doesn't really happen. So if we take a look at the chart here, you can see to take rid of the first electron, it's like 735 kilojoules of energy. To remove the second one, it increases, almost doubles. It's about 1,400 joules of energy. Now, if you want to rip off that third one, which is a core electron, you're now looking at about 6 times the amount of energy, and it's not going to happen under normal conditions. It's not energy favored, so it doesn't really happen. Also, why something like aluminum is +3, right? Because what happens after we get past that third electron, we are also into core electrons. And you can see the jump in energy from the third electron to the fourth is almost fivefold, right? So that's a lot of energy to try to remove that fourth electron. And again, it doesn't happen. So this is also why certain things have certain fixed charges, because once you run through those valence electrons, you're into the core electrons. You don't run into so much of a problem in the transition metal region because they have a lot of valence electrons, right? So, like I said, if you wanted to run through zinc's valence electrons, you got to maybe run through 12 of them, right? It probably is not going to happen. So that's why we also get a variety of charges for things in transition metals, because we have just a greater amount of valence electrons available to us. It's going to be a little bit easier to kind of remove those. For like iron, we could take off two, and it's not too much trouble to pop off the third one if we wanted iron with a +3 versus an iron with a +2 type of charge. Any questions on that there? All right. Here's a lot of other properties of transition metals, some of which we talked about. Again, electron configuration, we do see overall size as we go to the right on the periodic table decrease. Obviously, we see an increase in ionization energy from the first to the second to the third. We also see our common oxidation states of +2 and +3. Melting point and density sort of increases as you go to the right as well. And there's a graph again of first versus second versus third. Again, much harder to remove the third than, say, the first electron in each of those. Electron affinity. Electron affinity is the uh, energy change that occurs when somebody gains an electron. So, like we talk about sort of ionization energy being associated with positive and cation formation, we associate electron affinity as being with our anions. Because if somebody gains an electron, they're going to be negatively charged. It is in general increases as you go up and to the right and decreases as you go down to the left. It is not a perfect trend, as you can see here in group 7. Kind of increases as you go up, then kind of comes a little bit back down towards the top. So it's not a perfect trend, but it does go that way. This is the actual energy change that occurs when it gains an electron. Should not be confused with electronegativity, which is the ability of an atom to bring electrons towards itself. That also increases, right, as you go this way and decreases as you go this way. And our friend fluorine is the most electronegative atom that you could have. So these things do sort of relate to each other. Obviously, if you have a high electronegativity, you're going to be pretty good at bringing electrons towards itself. You probably will have a fairly high electron affinity as well, because you're going to be probably pretty good at taking that electron away and gaining it as you go through it. This is our relative reducing abilities of our first row transition metals and our potential here. And you can see reducing ability increases. And reducing ability means that it is going to be oxidized, right? And you may be saying to yourself, that doesn't make sense based on what we just talked about in the last chapter, because my SRP value there is the one that's more positive should get reduced, right? And if this is a better reducing agent, it's getting oxidized, it looks a little backwards to you. But you may also notice that these reactions are not reduction reactions, but they are all oxidation reactions. So what you're looking at here is like an SOP, the standard oxidation potential rather than reduction potential. If we were to reverse all these reactions, if we threw the reverse sign on everything here, we would have to change the sign for all these guys, right? And now all these guys would be negative if we made it into an SRP. And the guy on the bottom there would be more positive, and now it makes a little bit more sense. Our more negative guy is going to be oxidized, or anode. The guy on the bottom is actually more positive. He's going to be our cathode in that case. So this is, again, the opposite of an SRP sort of table. This is an oxidation table. All right. Here's what each of those first row transition metals look like, in case you need to pick them out in an ID or something like that. As you could talk about, and it's not so important for us these days as we don't do these type of experiments here anymore, but these are some common sort of oxidation states that they make, and they can make, obviously, you can see some different colors depending on the oxidation state of the metal that's present and the complex that they make, and these are just some examples of that. All right, now that we sort of hopefully review some of that stuff that about transition metals that you should hopefully know, let's get into really the heart of the chapter, which is about coordination compounds. And a coordination compound is basically kind of two things, and you could kind of think of it like an ionic compound. It pretty much is an ionic compound. A coordination compound is made up of a complex ion and a counter ion. So you have a complex ion, which is a metal in the middle that has a bunch of ligands attached to it, and you have a metal or some type of ion that's what is referred to as a counter ion, which essentially balances the charge of the coordination compound. So you will have a complex ion and a counter ion, and you can have a positive complex ion, which means you will have a negative counter ion, and vice versa. You could have a positive counter ion, and you could have a negative complex ion. It is very similar to an ionic compound, right? Where we obviously have a positive ion and a negative ion. And by the way, just like in an ionic compound, we always do the positive guy first and the negative guy second. So when we name these things, when we write sort of everything that's involved with it, it's always positive guy, then the negative guy here. So it is possible for each of those things to either be positive or negative. A complex ion, again, is a metal cation. Again, a lot of times a transition metal. Because it is positively charged, it is electron deficient, which makes it a really good Lewis acid, which is something that can accept electrons. These guys out here, as I mentioned before, these are good Lewis bases, which will donate a pair of electrons. What makes something a good Lewis base is if it's able to donate electrons. It may have a negative charge, and typically you get a negative charge because you've gained some electrons, or you're a polar compound or molecule that has some non-bonding electrons, makes it really helpful. So negative charge things or things with non-bonding electrons are really good in terms of being Lewis bases. So things like water is a Lewis base, ammonia, chloride, carbon monoxide here are also good Lewis bases, and these are all good ligands. Now, when we talk about ligands, they do have different donor atoms. And when we talk about what is the coordination number is how many atoms are directly attached to the metal in the complex ion. So, how many atoms are directly attached there? And it does depend on the type of ligand you have. So, you can have one that has a only one donor atom, and that is what is sometimes referred to as being monodentate, or some books call it unidentate. And that basically means you get one bonding per molecule. So one atom will bond to the metal in the complex ion only. So if you had something like water, ammonia, or chloride, and you had that cobalt there in the middle, it is only going to attach, for example, through the oxygen here. So in the water molecule, that would give you basically a one for one in terms of coordination numbers here. There are certain things that are able to bind in two places per molecule. That is what is referred to as being bidentate. Ethylendyl oftentimes abbreviated as EN. So if you see EN, it stands for ethylendyl. And that is something that looks like this. If I remember a little organic here, do something like that. There. And I feel like I need a couple of hydrogens there. So that is ethylendyl. That's En. And if you had a metal that was going to attach to, unlike water, which will attach in only one place, if you had a metal ion in the middle, some type of metal guy that has positive charge, through this nitrogen, this guy's able to attach, and through that nitrogen, it is able to attach. So you get basically a 2-for-1 situation happening here. For every one of those sort of ligands, you get basically two coordination number bump on it. Yeah. So if you had something like CrEn2, that is two of these guys, and that means you would have another one over here. And if this was my chromium, we would have 1, 2, 3, 4. The coordination number here would be 4. Sometimes people, when they identify coordination numbers, they kind of want to roll with this number on the bottom and go, it's probably that number. And it will only be that number if it's monodentate. If it's not, then you might have to adjust. The coordination number here would be 4. Another common bidentate one that you come across a lot is our friend oxalate, C2O42 minus. That also is bidentate and does pop up a lot. Oxalate looks something like this. A little carboxylic acid on each side here. And it is through both of those single bonded oxygens that they would attach to the metal ion. So that is where the attachment would actually occur in this particular case. Now, there's even things that combine in many, many places. They're sometimes referred to as being polydentate, and EDTA is an example of that. For every molecule of EDTA, there's like 6 different places within that molecule that will attach to the metal. So it really just grabs around the metal really, really good. So it's able to surround the metal very, very, very well because of that. Because in this case, again, it has about 6 different locations where it can do that. So it's important, especially when you're doing coordination number, to understand, is it a monodentate, bidentate, or something like that ligand? And again, if we look at the one that we had over here, each of these guys are monodentate. So each of the NH3s are only going to attach through the nitrogen. and that would give us one coordination number, two coordination number, three coordination, four coordination number. And obviously, chloride's only one atom, 5 and 6. So this would have a coordination number of 6, as it has 6 atoms directly attached to the metal that's in the complex ion. Two chlorides and basically four nitrogens directly sharing electrons, basically, with the metal that's in the middle. Any questions on that there? Now, how many ligands do you typically get? It does kind of depend on what is present, but a lot of times the charge does indicate maybe how many ligands you could get on there. If you have something with like a +1 charge, you're probably going to end up with a coordination number of 2, maybe 4. It's not as electron deficient as, say, something with a +2 charge, where you're going to most likely get coordination numbers of 4 and 6 happening. And then if you get to +3, which is really electron deficient, means it's a really good Lewis acid, you're going to get a lot of Lewis bases coming in because it has a very high positive charge, which means it's missing a lot of electrons, able to accommodate a lot of electrons coming in. And you oftentimes will get a coordination number of 6 for those guys, and except for gold, which typically will roll with a coordination number of 4. Here again is the picture of ethyl endyl diamine. Here's the picture of EDTA. As I mentioned before, one molecule of EDTA, which is everything on the outside here. 1, 2, 3, 4, 5, and 6 different places where that one molecule will surround the metal. These guys, bidentate and polydentate guys, are sometimes referred to as chelating agents, which means that they can basically just gobble up the metals and keep them surrounded. If you look at a lot of ingredients on things, you'll sometimes see EDTA mentioned in it, and it's used again for that reason, to sort of grab up a metal or something like that and kind of keep it trapped. Here are again some common ligands. Up on top are monodentate or unidentate, and again things like water, cyanide, nitrite, hydroxide, thiocyanate. Any of the halogens are really good ones. There's our two kind of common bidentates. So you get again two coordinations per one. Polydentate. Here's one that's actually diene. It says diethyl endyl triamine. That means it actually has 3 nitrogens, and each of those nitrogens will attach to a metal. So you get like a 3-for-1 deal here. You get 3 bonding per every molecule, as opposed to a 2-for-1 here and a 1-for-1 here. Actually, over here, this is like a 6-for-1 down here with our ethyl endyl, our EDTA here. And there's the big name right there of that. And you can also see that it's got some negative charges happening over here at the oxygens in this particular case. All right. Okay, we're going to continue on lecturing here. So, all right. So we been talking about sort of complex ions and coordination compounds. So for each of these, why don't you identify the oxidation numbers of the metals? And we're looking for the metals involved in the complex ion part. When they are written like this, usually the one that is in a bracket like so, that usually is your complex ion part. So why don't you take a moment and figure out the oxidation number. Okay, let's take a look. So once again, as I mentioned, usually kind of in these brackets is our complex ion. That means, by the way, over here outside of the brackets is our counter ion. So remember, in a coordination compound, you have both a counter ion and a complex ion. If we take a look here, hydroxide is -1, and there's four of them, gives us a -4. Potassium is group 1, which means it's +1. Obviously, here we are neutral, and that means that the gold here is going with a +3 oxidation state in this case. Questions on that one there? Coming to our right here, again, in this case, this is our complex ion, and this is our counter ion right here. So, kind of same idea. NH3 is neutral, which is 0. That is nitrate as our counter ion, and there's 3 of them, which gives us a -3. That means here that the chromium is going to be +3 in this particular case as well. First off, any questions on the oxidation states here? In terms of the coordination number, this is going to have a coordination number of 4, as the complex ion part has basically 4 hydroxides attached to the metal. Each hydroxide attaching through the oxygen gives us a coordination number of 4. Over here, we have ammonia, which is unidentate or monodentate, attaching through the nitrogen. Coordination number would be 6 for the complex ion. Any questions on that one there? So here we have basically on both of them only monodentate ligands, which can attach 1 per 1. Now, if we look at this a little bit more closely and we just take the complex ion part, now that we know the charge on the gold, that is -1, which is -4. That's a +3. That means in this particular case, our complex ion is actually negative overall. It actually has a -1 charge overall. That is why when we look at our counter ion, we only have 1 potassium present. And just like in an ionic compound, when you add up all the positive and negatives, it needs to equal 0. And that's what we get here. And that's why, again, we only need 1 counter ion of the potassium. If we take a look at our complex ion part of this coordination compound, we have +3 for the chromium, 0 for that. That means that our complex ion in this case actually has a +3 charge overall. That is why in this particular case, when it comes to the counter ion, we need not 1 nitrate, not 2 nitrates, but we actually need 3 nitrates to give us a -3 charge to balance out the +3 charge here of our complex ion. So this also demonstrates these two examples, what we talked about at the very beginning, which is in the first example, our counter ion is positive and our complex ion is negative. In the second example, complex ion is positive, counter ion is negative. So they can be either one. You actually know the charge of the complex ion by its position in its formula there. So since the complex ion comes second, we do know it's going to be a negative overall complex ion. Because it comes first in the second one, we know it's going to be positive. Always positive, then negative when we do these coordination guys. Any questions on that there? All right. So I know you probably thought naming was all done for you in your chemistry career, but here we go. Let's talk a little bit about naming these things. So naming these coordination compounds, as I mentioned before, when we name it, we do go positive guy, then negative. So the cation is named first and then the negative guy. Within a complex ion, the ligands are put and named in alphabetical order, regardless of prefix. So there happens to be a prefix. We don't, you look at it in terms of alphabetical order. We just look at the first letter. Some ligands will end with the letter O. Some neutral ligands will just be called the same name it normally is. And there are some exceptions, like water is known as aqua, or depending on your book, aqua. CO is carbonyl, NH3 is amine. So there are some special names for certain ligands. If we have multiples of the same ligand in the same compound, We do use some Greek prefixes like di for two, tri for three, tetra for four, penta for five, and hexa for six. All right, two, three, four, five, and six. Now, if by some chance the ligand itself already has a prefix in its name, we then will roll to some other prefixes, if we have multiples, where we will use bis, which is two, tris, which is three, tetrakis, which is four. Now, it does sound like maybe people are making this up, but maybe not. An example of that is actually the one that's abbreviated most of the time with EN. That is ethyl endyl diamine, because it has the word di in its actual name. If you have more than one of those, say you had two of them, you would not use di-en, you would use bis-en. So there are certain ligands that actually have a prefix as built-in part of their name. Another one like we saw earlier where it was that one that was basically triamine at the end. So tri is a prefix. You would again use this sort of different ones along the way. I will say, sort of an exception that sometimes people will also use that type of prefixing is if you have oxalate because it is polydentate. So sometimes they will use that if you have more than one oxalate. You could use the regular prefixes, or like sometimes people will use the other one as well. The oxidation of a number is actually written with a Roman numeral, followed by the metal. Um, Now, the Roman numeral is used when we name these type of compounds always. So even for things that normally have a fixed charge, like silver, zinc, those type of guys that we normally do not use Roman numerals for, we actually still use them for those type of ones in this type of naming. In addition, as weird as it's going to sound, you can get yourself a neutral metal with no charge, and you would use zero for that as well. So we will use like a zero if something has no charge. So we definitely use Roman numerals a lot. This part of it, by the way, as I mentioned earlier, we do go alphabetical for the ligands, and the metal part or the metal atom is always the last part of the complex ion name. And what I mean by that is not necessarily always the last part of the name. It is the last part of the complex ion part of the name. So that's always where it should be. If the complex ion is negatively charged, so if your complex ion part of your compound is negatively charged, you will actually use more like the old school name for the metal that ends in ate rather than kind of the regular name. So, for example, instead of copper, you would use cuprate. Instead of iron, you would use ferrate. So, plumate for lead and so forth. So, if it is a negatively charged complex ion, you kind of go old school name with the ate ending on it rather than the regular name. If your complex ion is positively charged, you just roll with the regular sort of metal name like you normally would name the metal, basically. So here's some tables of some of these ligands and some of the names. Again, aqua or aquo, amine, methylamine, which is the regular sort of name for that, carbonyl. Our halogens are named like we do in organic: fluoro, chloro, bromo, iodo, cyano for cyanide, hydroxo for hydroxide. And here's what I was talking about. If you do have a negative complex ion, we again kind of roll with the old school name instead of iron, ferrate, cuprate, plumate, argentate for silver, aurate, and stannate, for example, for tin. So kind of like the older version of the name with ATE at the end of it. Here's some other common ligands. If you got carbonate, a little carbonado, a little oxalato in case you're ordering coffee, a little aquo, and these are our ethyl, that's our EDTA down there. And that's obviously quite a big name as you go through there. All right, so let's go back, for example, to like these two here that we just did. So if we were going to sort of name these guys, we would go through our sort of process here. We would probably do very similar things that we just did in this question to figure out oxidation states, and obviously, is our complex ion positive or negative? So we clearly see in the first one here that we do have a negative complex ion, and we do have a counter ion. The good news about the counter ion is it's pretty much just the name of it. So it doesn't matter how many you have of it, you just call it whatever it is. So this would be potassium. If you had two potassiums, it would still just be potassium. Just like if you had like K2O, that's potassium oxide. It doesn't matter how many potassiums you have, so it's potassium as well. So good news on the counter ion, it's just pretty much the name of it. It would be a metal most likely, or it would be a complex ion or something like that, or an IDE type of negative guy. Now, because this is a negative complex ion, we will not use gold. We will have to use the sort of older version there of gold name, and that is arurate. And again, instead of gold, because our complex ion is negative, we're going to go with the arurate. And what we know from what we dissected here, we have arurate Roman numeral 3 for the charge that's on it. Now we also have 4 hydroxides here. Prefix for 4 is tetra. And once again, it's not called hydroxide here. It is hydroxo, as you can see here. I think it's on this slide. Yeah, it is right there. Hydroxo. So that is what we're going to use there. And tetrahydroxo. All right, so now putting this together, this would be potassium. Now we're into the complex ion part of the name. We start with the prefixes, or the ligands, tetrahydroxo, arurate, Roman numeral 3. So this would be potassium, tetrahydroxo, arurate 3 is the name of, obviously, our original guy here together. Any questions on that name? Now, if we take a look at this second one, we already sort of dissected it and found out that the complex ion here is positive, which for the metal is good because we could just roll with the regular name of our metal. So this is going to be chromium, Roman numeral 3, because the complex ion is positive. Here we have 6 of these NH3s. Prefix for 6 is hexa. And again, NH3 is amine. If you look it up on that table there, that is basically the name for NH3. And then here we have multiple nitrates. And once again, that is our counter ion. So it doesn't matter how many we have of it. It is still just going to be called nitrate. So once again, putting this in order, ligands first. So hexaamine, chromium, Roman numeral 3. Running out of room, I'll go underneath, nitrates. Yeah. So hexamine, chromium 3, nitrate. Any questions on those names? Now you may be asking yourself, or you're probably not asking yourself this, but maybe one day you might. What happens if I just had just the complex ion by itself without the counter ion present and I wanted to name it? If you just had the complex ion by itself, you basically just use the complex ion part of the name, and then you just throw the word ion at the end. So if you had just the complex ion by itself, that would be tetrahydroxoarurate 3 ion, because you don't have a counter ion present. So you basically name it the same way if it's just the ion by itself. Any questions on that there? As you can see, you need a lot of room sometimes for some of these names. I might go over the page. All right, now that I had fun on some, why don't you have some fun maybe-ish on some of these? Okay, let's take a look. So once again, when we sort of analyze this, this is our complex ion. That is our counter ion. And just from sort of the location of how that is in the formula, we do know our counter ion should be positive. Our complex ion actually should be negative in this case. So we do want to kind of figure out some oxidation states of our metals. That is oxalate, which is -2. There's three of them, which is -6. That is our +1 for our potassium, but there's three of them. Gives us a +3. So we have a +3 and a -6. Again, this counter ion or this coordination compound is neutral. That means the chromium here would be +3 as well. By the way, the coordination number of this guy would be, coordination number is 6. So this is bidentate, which means you get 2 for 1. It will attach at 2 oxygens per. That means you have 6 atoms actually attached. Does not equal the little subscript on the bottom. So again, depending on the ligand, it may be different. So a couple things we do know is, frankly, our potassium is all we're going to call that first guy. Because our complex ion is negatively charged, that means instead of chromium in this case, we would use chromate, M-A-T-E. And it would have a Roman numeral of 3. And once again here, oxalate is not called oxalate. It is, as you can see here, oxalato. And we do have 3 of them. So that is trioxalato. Now, this is one where people will sometimes use tris because it's bidentate, oxalato. And I think that's everything that we need. So kind of putting it together here, we got a little potassium. And again, it doesn't matter how many of those counter ions we have. We're just going to use the name. We're going to go with, you could go trioxalato, chromate 3. Or obviously, as I mentioned before, sometimes people will use potassium. In this case, tris oxalato chromate 3. I would say kind of oxalate's one of the few ones that kind of go either way, and sometimes people do either one. Any questions on that one there? Yeah. Because that is the name of the ligand here. So if it's oxalate, it's called oxalato in this type of naming. Just like ammonia is not called ammonia, it's called amine here. And, there's some different names for ligands. So, other questions? All right, we'll try a couple more here. Top one, let's go name. Bottom one, let's go formula. Also to the left, there's a few more. Okay, so let's take a look, see how you're doing. We'll start with the name. Once again, looking at the name or the formula, as you look at the formula, we do see our complex ion comes first. So that automatically kind of tells us it probably should be positive. Here, the Cl would be our counter ion in this case. We do want to kind of figure out what we got going on in terms of charges. So water is 0. That is -1 for the chloride. There are 2 of them, which is -2. We also have another chloride on the outside, and that's going to give us a grand total of kind of a -3 overall charge happening. That means that the chromium in this case is going to be +3. I know we hit a lot of +3s, but they're not all threes, but it is a common sort of oxidation state. Any question on that there? Also, a benefit of our complex ion being positive, we can just use the regular name of chromium rather than the kind of the older school name. So we definitely have a chromium Roman numeral 3 happening. We have 4 waters, so the prefix for 4 is tetra, and water aqua, your choice. We also have 2 Cl's within the complex ion, so that is a dichloral. And then obviously here our counter ion is just named like we normally would, and that is a negative chlorine, which means it would be chloride and not chlorine. So it's a negative version. All right, so we just need to put it in together here, alphabetical order in terms of our ligands. And we do alphabetical order regardless of prefix. So we would be comparing the C to the A here and not the prefixes. So that means that we would actually go with our A first. So that's tetra aqua or aqua. Dichloral chromium Roman numeral 3. Yeah. Any questions on that name there? Yeah. Oh, I'm sorry. I should put the chloride. Thank you. I forgot it there. I got lost looking at that. Thank you. It should, and obviously our counter ion there, which would be chloride in this case. Um, so tetraaquo dichloral chromium 3 chloride. Without the chloride there, it would just be that with ion at the end of the name. Coordination number on this one is 6. 2 chlorines attached and 4 waters attached are all monodentate. So the coordination number here is going to be 6, equal to the subscripts in this particular case. Any questions on that? Now we want to write the formula. So we got a little tris ethylendyl diamine. So ethylendyl diamine is EN is the abbreviation. It actually is used both in formula and name. Remember that is this guy here, which I guess you could write out if you chose to do so, but most people will just use the EN. Tris is the prefix for 3, and that is because within this name it says di, so that's using that other prefix version. Cobalt with a Roman numeral 2 means the cobalt has a +2 charge, and our sulfate here is our counter ion, which is over here. I know the sulfates are counter ion because the metal always comes at the end of the complex ion name. So cobalt 2 is the metal. At the end of that is a complex ion. So putting this together, I have CO and I have 3 of these guys. And at this point, I might want to figure out what is the charge on the complex ion by itself. So since En is 0 and this is +2, that means that my complex ion right now, without a counter, should have a +2 charge. The reason that's important to know is that tells me how many counter ions I need. So since each one is -2, we want to get to 0. I frankly only need one of those guys, and we will end up with something that looks like so, yes? Again, our 1 sulfate, which is -2, to balance out the +2 charge of the complex ion. Yeah. Any questions on that there? All right, let's try a couple more for fun. Not really fun. I don't know. We'll see. We'll go names on these here. Telling us it's positive. Once again, here, chloride as our counter ion, which will be negative. Doing our charge, so NH3 is 0. We got 1 Cl minus inside. We got 2 on the outside. So again, giving us a -3 overall. When we put those together, going to be balanced by the +3 for our cobalt. So since this is a positive complex ion, we can just use cobalt, Roman numeral 3. We have 5, which is penta. Ammonias, which is amine, is the name for it. We do have 1 chlorine or chloride inside. It's just going to be chloral. We actually do not use mono for 1, so we don't use the mono name kind of on this. So we just use chloral. And we're going to go alphabetical here. Once again, we're looking regardless of prefix. So we're going to go A first, followed by C. So that's going to be pentamine, chloral, cobalt 3. And I won't forget it this time. Counter ion going to be chloride in this case. Yeah. Any questions on that one there? Yeah. Um, it's possible somebody could write it that way. Most of the time, when you're kind of going backwards, you might want to just kind of put it back in alphabetical order. So I won't say it's possible you might see somebody kind of do it by accident or not that way, but um, a lot of times they will kind of follow what's in there, and that should hopefully be kind of alphabetical order. Other questions? Yeah. On the outside, no. So for the counter ion, it doesn't matter how many you have. You just use the name of it. So if it's a polyatomic ion and you got 30 of them, you just use the name of it. If it's a negative ion like chloride, whatever it may be, bromide, whatever it may be, you just use that. Or if it's a metal and you have multiple of those up front, it doesn't matter either. So you just use the name. Yeah. So, other questions? Coordination number on this one is also going to be 6, as we have 5 monodentate ammonias and 1 monodentate chloride there. Coming to the second one here, we got our counter ion that's coming first, which is going to be positive. We got our complex ion coming second, which is going to be negative. So again, figuring out oxidation state, that's -1 for cyanide, and that's -6 overall. On our counter ion side, we have +1, and there's 3 of them, which is +3. So once again, here we get a +3 for our iron. Because it is negatively charged, our complex ion, that's going to be ferrate 3 instead of iron 3. Hexa for 6, and cyano is sort of the name there for cyanide. And again, here we have 3 potassiums for our counter ion. Doesn't make a difference in terms of the name. So this is going to be potassium, hexa, cyano, ferrate 3. In this particular case, yeah. Coordination number on this one also going to be 6 because those are monodentate as well. Yeah. Any questions on that there? All right, and a couple more formulas here to finish this little section out. Okay, let's take a look. So here, we're just gonna kind of dissect a name. We have triamine. So amine is ammonia, so that's NH3, and tri is 3. So we got 3 of those guys going on. We have a bromol, which is a Br minus. And we have a platinum with a Roman numeral 2, which means we have a platinum PT, there you go, with a +2 charge. That is basically our complex ion part. Remember that always in the complex ion part of the name, the metal will come at the end. So that's how I know that's sort of the end of the complex ion part of it. So if we just kind of put together our complex ion, we got our PT, we got our NH3, and we got 3 of them, and we got our Br here. Here we're gonna again kind of figure out what is the overall charge of our complex ion. So the platinum is +2, that is 0, and that is -1. That means in this particular case, if we just looked at the complex ion part, we will end up with a +1 overall charge. And that's important because here this is our counter ion. And our counter ion in this case is chloride, which is -1. And that basically tells us to get to 0, we just need basically 1 of each. And that would get us something that looks like this, maybe. Any questions on that one there? Coordination number of this one would be 4 in this case. 3 ammonias each attach one place and 1 bromine there that also attaches in one place. So the coordination number here would be 4. Any questions on that one there? Taking a look at the last one here, we're going to also dissect it. Here we see potassium coming first. We see hexafluorocobaltate 3. That is the metal part of the name, which means this part here is our complex ion. And this part up front is our counter ion. So we know right off the bat our counter ion is K+. Hexafluoral, that's fluorine, and hexa is 6, so you got 6 of them. Cobaltate, that is the negative version of cobalt because the complex ion is negative, so we have a cobalt with a +3 charge here. So again, if we just kind of build our complex ion part, We have a cobalt with 6 fluorides. And this guy being +3, each one is -1. There's 6 of them, which is -6. And +3 means that our complex ion in this case is carrying a -3 charge. That means in the case of our counter ion, we don't need 1, we don't need 2, but we actually need 3 of them there to balance it out. And that would give us something like K3COF6 in this case here. Question on that one there. With a coordination number of 6 in this case, as fluorine and all the halogens are monodentate.